For section 2.3, we're now going to be looking at what's called the factored form of a quadratic function. We've looked at vertex form and standard form. The vertex form has revealed the vertex for us very quickly. Standard form has revealed the y-intercept form for us very quickly. And now we'll see what the factored form can bring for us. So this critique can explain what I did, and you can solve that, check your teacher's answer key, but I graphed all three of these to see if they were the same. And as I show the next slide here, you'll notice on Desmos, each of my equations was graphed in a different color. They're all turned on, and you only see one graph. So we're going to be able to know it's the exact same equation. Now, if we look at all three types, this is our vertex form. This is our standard form, and this will be called our factored form. You can watch the previous video on factoring, or you learned factoring in Math 2, and we'll be using it a lot. Students often struggle because there's so many ways to factor, but lots of practice will make you better. If we look at the factored form, one thing we can note from standard, remember we had the y-intercept very visible. It does appear that it's definitely negative, and likely negative 16. Our vertex here would be -3, -25, and while I didn't click on that, or it didn't show us that, it does appear it's happening at like -3 and about -25. And finally, our factored form, we're going to see what that reveals to us in this graph. Looking at example 1, they just want you to practice factoring. We're not going to do this one together, but you can check the answer key and use that worksheet that you had from class yesterday or the previous to this video and practice factoring these in whichever method you think worked best. Now on example 2, here's where we learn why factoring is so important. If we look at this x squared plus 2x minus 8, I know that it factors with two parentheses. I know x times x is x squared. And I know 4 times 2 is 8. But one of them needs to be negative to make it become a -8. I'm going to make my 2 be negative because I know -2x added to 4x would make 2x. So now it asks us to look at the x-intercepts. And if I go over to the graph, I see it crossing at a +2 and a -4. If we look at our factored form, do we see how that might have come to be? Again, I'll write down my x-intercepts here. If you look at your factored form, you're able to maybe see a pattern. Notice how -4, if you plug it in for x here, -4 plus 4 would make 0. Or if you plug 2 into this one, 2 minus 2 would make 0. That's definitely why we call our x-intercepts the zeros. Zeros and x-intercepts are the same thing. They're where the graph hits the x-axis. So we could say that our x-intercept is the opposite, or essentially what makes our parentheses 0. So if I take x minus 2, which was one of my factors, and set it equal to 0, adding 2 to both sides tells me it crosses the x-axis at 2. If I take x plus 4 and set it equal to 0, set my factor equal to 0, I get x equals -4, and that too is an x-intercept. Now we see why factoring is so important. So if we look at this equation here, and I factor x squared minus 9x plus 20, x times x will make x squared. Multiplying to get me 20, I know 5 and 4 will, and I know 10 and 2 will. Well, 5 and 4 have a better chance of making a 9. So if I put a -5 and a -4, those would add to -9, but multiply to 20. So if this is my factored form, remember to find the zeros, I can even almost see it over here. My number that will make this become 0, x minus 5 equals 0, that's going to be 5. So x will equal 5. If I make x minus 4 equal 0 and add 4 to both sides, x will be 4. I can see that that does match the x-intercepts of that quadratic. Example 3 wants you to solve the same way we were by factoring, but notice how sometimes the equal sign is not in the right spot. So we need to do a little work. On this one, if we subtract 42 from both sides, it would give you x squared plus x minus 42 equals 0. When we're solving it equal to 0, that means we're trying to find the zeros of the graph, or the x values that we would plug in and make the equation be 0. You could guess these numbers, but remember, factoring makes it a lot quicker. So I would say x times x would be x squared. 7 times 6 would make 42, and if I make the 7 positive and the 6 negative, that would add to my 1x. So this would tell me that my solutions are x equals 6 and x equals negative 7. So I won't factor all of these for you, but just a couple movements here. Remember, you want to get everything on the same side. So I'm going to leave my 2x squared there. If I add 9x and subtract 5 to both sides, I'd get 2x squared plus 9x minus 5 equals 0. And again, you need to factor this. You could do it by grouping, you could guess and check, you can use your diamond and box. But remember, your goal is to find what number will plug in for x or substitute in for x to make it the equation equal 0. But factoring will save you some time if you don't want to spend that time guessing and checking. And then, of course, it also finds you where it crosses the x-axis. Here I would subtract 20 to give me x squared plus 8x minus 20 equals 0. And here we'd have 2x squared minus 3x minus 2 equals 0. It's important to always get it equal to 0 before you factor. So do that, then use any of those techniques from the worksheet to get your factoring done and solve for when it equals 0. Just for fun, we can try this last one here by grouping. So remember, we take our first and our last term to multiply by each other, and I put that at the top. So I would take negative 2 times 2x squared to give me negative 4x squared. Then on the bottom goes my middle term, negative 3x. I want to think of two terms that multiply to give me negative 4, but add to give me negative 3. So if I go negative 4x and positive 1x, that will multiply to negative 4, but add to negative 3. So now I come over here and I rewrite my first term and my last term out, and I fill it in with my green minus 4x plus 1x. And you can put those in any order you like. But for grouping, we're going to group the first two together and the last two together. My first two, they both have a common term of 2 and an x. And so I would say 2x times what gives me 2x squared? I just need the x. And 2x times something to give me negative 4x would be my minus 2. And so now I can say my 2x would be factored out, and I have x minus 2. Over here, there's no x in both of them. 2 and 1 have no common terms besides a 1. So if I pull that 1 out front, I'd have x minus 2 to give me that x minus 2. Now, to continue on here, we would say that I want to take out what's in common, that bubble, if you will, that I have in common. Notice how I have x minus 2 and x minus 2 there. So I'll take out that x minus 2 in the first term, and then whatever's left over we write in a separate bubble. So 2x will go here, and plus 1 will go here. And I'll set it equal to 0. The tricky part is you get done factoring and you're still not quite done. So I need to be thinking, what will make these each factor be 0? So x minus 2. I'm going to do this one by hand. If I put 2 in, 2 minus 2 would be 0. So there's one of my zeros. But now this guy has an a value. So I'd say 2x plus 1 needs to be 0. I'm going to subtract 1 from both sides, and I'd get 2x equals negative 1. I'll divide by 2. X will be negative 1/2, or negative 0.5. These are the two x values that if you plugged back into the equation in the beginning, they would both be equal on each side. Or if I graph this parabola 2x squared minus 3x minus 2, that would be where it crosses the x-axis and makes that equation 0. With the real-life application, they give us an equation of a gentleman hitting a golf ball, and they want to know when it hits the ground. So imagine if this was a parabola and it continued, it's going to hit the ground. Well, look, if that was an actual parabola, we would have an x-intercept out there. It would be a 0 of the function. So you're basically going to need to factor that equation, and you want to know when it's going to equal 0 or have a y value of 0. which is your x-intercept. So we could take out a negative 16 first. If you're ever able to take out a common term, it will make your job a whole lot easier. So we'd have a minus 2 here. You leave your negative 16 for now, and you're going to think what multiplies to x squared, that'd be our x and our x, and what multiplies to negative 2 but adds to positive or to negative 1, that would be 2 times 1, negative 2 times 1. And now our zeros, we would say when x equals negative 1, this parabola would cross the x-axis, and when x equals positive 2, it would cross the x-axis. However, remember it's a real-world problem. It's x seconds after it leaves the ground when he hits it. We wouldn't have negative 1 seconds be a thing. That would actually be back if he would have hit from back here. Okay, but 2 will work. So we would say after 2 seconds, the golf ball will hit the ground. Another application problem under the try it, if you want to try that and check the answer key is available. And then finally, on example 5, they want to know when would this parabola be positive. You might be thinking, this is like the 1-1 section we did. Positive would be above the x-axis. If we can sketch this graph and find when it hits 0, and note that it's a happy parabola because of the positive x squared value, we can tell when it's above the x-axis or positive. So I'm first going to start by finding out when it equals 0 by factoring. And if I write the equation and set it equal to 0, I'm going to factor quickly. X times x is x squared, and 3 times 1 is 3, but if I make this a negative 3 and a positive 1, I'll add to negative 2 when I multiply the middle and the outside terms. So I know my zeros are at negative 1 and positive 3. That's where this parabola would cross the x-axis. So I'm going to put a little dot at negative 1 on the x-axis and a positive 3. And I know it's a happy parabola because my a value is positive. So I'm just going to sketch the graph. I could have taken care, and I actually did do a pretty good job there. I hit the negative 3 on the y-axis. And that's important because that's what we get from our standard form. And so now I know this graph is upward facing with x-intercepts at negative 1 and positive 3. When is the graph itself positive? Well, that's when it's above the x-axis. So that would be right here and right here. So remember back to 1, 1, when we answer this in interval notation, we would say it's positive from negative infinity up to negative 1 and from 3 to infinity because it's above the x-axis. We didn't have to sketch super specifically, but with all of our knowledge from factoring to find the zeros, a value telling us it opens up, and knowing the y-intercept is negative 3, little bonus there, we can tell when the graph is positive and answer with our interval notation.